Hi everyone, my name's Dana Clark and I'm a marine ecologist from the Cawthron Institute in New Zealand. Our coastal environments are under increasing pressure, so it's critical that we've got good monitoring tools that can detect early signs of degradation to enable us to better manage these important systems. And while metabarcoding is rapidly expanding as a new approach to biomonitoring, much of our understanding of the suitability of this approach relies on correlative studies or experimental research that's carried out in labs. Manipulative field studies are required to prove cause and effect and also to demonstrate that any changes that we're seeing would be able to be consistently detected above natural variation once we go outside and apply these tools in the real world. In our study, we wanted to know whether eDNA metabarcoding could be used to characterise changes in benthic communities in response to nutrient enrichment in estuaries. Nutrient loading is a major threat to estuaries worldwide. 2/3 of estuaries in the US have moderate to high levels of eutrophication, and 1/3 of European estuaries are affected by enrichment. So in order to answer this question, we set up manipulative nutrient enrichment experiments in 2 estuaries here in New Zealand. The 2 sites were quite different. So in one estuary we had a sandy site that was located close to the estuary mouth in quite a dynamic environment. And our other site was located here in this estuary, and it was in a more sheltered location, so the sediments here were muddier. At each of the sites, we added nitrogen fertiliser to the sediments to simulate increased nutrient loading to the estuaries. Each site had 3 treatments, and each treatment had 3 replicates. So we had a control treatment where we added no fertiliser to the sediments, as well as medium and high treatments, which had medium and high amounts of fertiliser. So these nutrient additions were designed to be consistent with the levels of nutrient loading you might expect to see in estuaries. Then we left the sites for 7 months and we came back and sampled them to see what effect the enrichment had. From each plot we took 5 small sediment samples for eDNA analysis, 2 cores for traditional macrofauna analysis. We also looked at the sediment pore water to check that the fertiliser had actually enriched the sediments, and we collected a bunch of other samples to look for differences in sediment properties. For the eDNA metabarcoding, we wanted to compare the performance of 3 different indicators for picking up these nutrient effects. So these markers use different sets of primers to target different communities. So the 18S marker targets eukaryotic organisms. So similar to a traditional macrofaunal sample, this is going to include things like shellfish and worms, but it's also going to pick up smaller taxa like myofauna, which wouldn't normally be captured by conventional sampling. We also wanted to look at bacteria and diatom communities, which because of their high turnover rates are expected to respond more quickly than macrofauna. So these could be good early warning signals of disturbance. And we used 16S and Rubisco as markers to target these communities. So when we went back to our sites 7 months later, we found that the nutrient addition had worked, and sediments in the high plots were now comparable to what you might expect to see in a eutrophic estuary. So there was big differences in the nutrient levels between the 3 treatments, but no significant difference between the 2 sites. In contrast, when we looked at other sediment properties, the nutrient addition had not affected them, although these were different between the 2 sites. So we can be confident that any changes that we're seeing in our benthic communities are indeed a result of our nutrient addition. When we looked at the benthic communities, the first thing we noticed was that there were distinct differences between the 2 sites. So if you're not familiar with reading PCO plots, each sample is represented by a square or a circle. And the closer these samples are together, the more similar the communities, and the further apart, the more different. So in these plots and the rest that I'll show, the squares indicate our sandy site, the circles indicate samples from our muddy site, and the different colours are the different treatments. So you can see that for all 4 communities, the greatest difference was between the 2 sites rather than between the 3 treatments. And this makes sense because we know that the environmental conditions at these 2 sites were quite different. In order to further investigate this nutrient effect, we looked at each site separately using a constrained ordination technique. So these plots are read in the same way as the previous ones, and you can see that samples from the same treatment are starting to group together, indicating similarities in community structure within that treatment. The values in blue are the classification success. So this is a measure of how well the model is able to correctly allocate a sample into its appropriate group. And it's a measure of how well the model performs. So in an example where, if you had 3 groups like we do in this example, you would expect a roughly 33% success rate just by chance. So you can see that all 4 of our communities are doing a good job of distinguishing between the 3 treatments with at least 67% success rate. And at this site, the macrofauna were the poorest at distinguishing between the 3 treatments, while bacteria and diatoms were the best. We found similar results at our muddy sites, so the eDNA-derived communities were better at distinguishing between the 3 treatments than the macrofauna. But at this site, the eukaryotic organisms were more sensitive than the bacteria and the diatoms. And these differences might arise from the differing environmental conditions at the 2 sites. And it also suggests that the development of any indicators may be context dependent. We also identified indicator taxa for each of our sites that were associated with each of the treatments. So these heat maps show bacterial indicator taxa across the 2 sites. And along the left you can see the taxa names along with the treatment or the combination of treatments that they were associated with. And the darker the colour, the higher the abundance of these taxa. So many of these indicator taxa were site-specific, and this fits with what we saw at the community level with this clear separation between the 2 sites. However, for the indicator taxa that were associated with the high treatment, there was actually quite a few taxa shared between the 2 sites. And this becomes important when we start to think about developing indicators that are broadly applicable. Most of these taxa were also absent in the control and the medium treatments, which suggests that they're favoured once nutrients reach a certain level. And this fits with what we know about the functions of these organisms. So they're associated with things like nitrogen and sulfur cycling, as well as the degradation of organic matter. So that's the types of changes we would expect to see in enriched sediments. Most ecological health assessment methods can easily distinguish between an impacted and an unimpacted site, but it's more difficult to discriminate smaller changes in health. But in our study we found indicator taxa that were specifically associated with low levels of nutrient enrichment. So this suggests that there's potential to develop indicators that could pick up subtle changes in health before our estuaries become too degraded. Before developing a new indicator, we wanted to see if existing indicators could detect the nutrient addition. So we tested 2 indicators that were developed using independent data. The microambi was developed in Spain using data from estuarine and coastal sites, and it's designed to detect anthropogenic impacts from a range of sources. It uses expert judgment to classify bacterial taxa into ecogroups. The bacterial metabarcoding index was developed in New Zealand to detect salmon farm impacts using data from coastal sites, and it uses regression splines to assign ecogroups. Even though these indices were designed for different stresses and developed using completely different methods, they showed a consistent response to the enrichment. So we saw a decline in ecological status with increasing nutrients at the sandy site, but little change at the muddy site. Given that neither of these indices were specifically designed to detect nutrient impacts in estuaries, I think these results are really promising, and they suggest transferability of these indicators to other regions and applications. However, they might need some adjustment, for example, to better reflect eutrophication stress in muddy sediments. So in summary, eDNA-derived communities show great potential for ecosystem health assessment. The best performing marker differed between the sites, so this shows that before we can start to properly develop these indicators, we need to expand the scale of the study to make sure any patterns that we see hold true across wider scales. And this experiment that we carried out was actually done at 22 other sites around New Zealand, so we can easily scale up this study. We also want to start looking at how these communities respond to other stresses, as well as start to link these structural changes to changes in ecosystem functioning. So this is the first step towards the development of molecular tools that could provide a more holistic and sensitive approach to estuary health assessment with rapid turnaround times and lower costs. So I'd just like to thank my co-authors and the funders of this study, and if you want to find out more, this work was recently published in Environmental Pollution. So thanks.